Here's an antiderivative that involves a different base. It's not base e, but we could always use our change of base formula. So one thing we could do is change base. Let's see, log base 7 is the ln of x over the ln of 7, and that's all squared here. Let me break it up and try to move the ln 7 part out of the way since it's constant. So we have dx, we have x, and we have ln of x squared all over the natural log of 7 squared. Let's see, here's my main fraction. So what I want to do is probably multiply top and bottom. Since we have a complex fraction, tiny fraction inside big fraction, let me multiply top and bottom by the natural log of 7 squared. Okay, so when I do that, I have the antiderivative of the natural log of 7 squared times dx up top. Down below, these cancel, so I have x times the natural log of x squared. Now the natural log of 7 is a constant. It's just a number. It's the exponent you put on e to get 7. That doesn't change as x changes. So this constant can come through. So we have the natural log of 7 squared times the antiderivative of dx over x times the natural log of x squared. At this point, you can notice that a good substitution to make would be u equals ln x. And the reason that's a good one is because then du is 1 over x dx, and you actually have 1 over x dx right here in the integral. So when we do our substitution, we get the natural log of 7 squared, and then dx over x, that's du, and ln x squared is u squared. So we have this constant ln 7 squared out in front of u to the negative 2 du, and we know what to do with the power. The power should increase, so we get u to the negative 1. We're going to need another negative, though, out in front, so that when we take the derivative, the negative 1 will come down and it will become positive. And now we can just substitute back. We have, let's see, we have a negative ln of 7 squared. U to the negative 1, u was ln x, so that's really 1 over ln x because it has a negative power. And we found the antiderivative here. One more example. This one is an initial value problem, right? It's a differential equation because we have information about the derivative of y with respect to t. We know how y is changing. We also have an initial value here, some initial data, because we know that when t is the natural log of 3, this says that if you plug that into this function y, out will come 1 over pi. So this is our initial data. We call this whole thing an initial value problem. So let's see, we know that the derivative of y with respect to t is this, so that means that y must be the antiderivative of e to the negative t, secant squared pi e to the minus t with respect to t. And you can see a good substitution at this point would be to let u be pi e to the negative t. If you do that, du is going to be negative pi e to the negative t dt. And we do have, because you can multiply in any order, we do have an e to the negative t dt already in the problem. There it is, right? E to the negative t is multiplying dt if you rearrange. So basically, negative 1 over pi du is equal to e to the negative t dt. With that, we can do our substitution. And let's see, we get the secant squared of pi to the negative t, that's secant squared of u. And then this e to the minus t dt is negative 1 over pi times du. If we pull the constant through, all we have to do is find the antiderivative of the secant squared of u. And the derivative of the tangent is the secant squared, so we get minus 1 over pi tangent u plus c. So what we've done is we've found, let's see, one more step. We know that y as a function of t now is negative 1 over pi. I have to substitute back. That's okay, now we've found a family of functions whose derivative satisfies this equation, right? So, but they all vary by some constant. Our question is, what particular member of this family, when you plug in natural log of 3, will 1 over pi come out of? So let's see. If we plug in the natural log of 3 into what we've found so far, we get negative 1 over pi times the tangent of pi times e to the negative natural log of 3 plus c. But that's negative 1/2 the tangent of, let's see, pi over e to the natural log of 3 plus c. All I did was, since that had a negative exponent, I took it downstairs so we'd have a positive exponent. And now we know that, oh, this isn't 2, that's a pi. Okay, negative 1 over pi. Now we know that e to the natural log of 3, the natural log of 3 is the exponent you put on e to get 3. So if you put that exponent on e, you'll get 3. So we actually have the tangent of pi thirds plus c. The tangent of pi thirds is root 3, so we get negative 1 over pi times the square root of 3 plus c. On the other hand, we're told that if you plug in the natural log of 3, you're supposed to get out 1 over pi. And that tells us that c is 1 over pi plus root 3 over pi, or that c is 1 plus root 3 over pi. With that, we can now go back to this function and find out exactly what y is. Y is negative 1 over pi times the tangent of pi e to the negative t plus this constant c, and now we know that the constant c is 1 plus root 3 all over pi. So we've found from this initial solution here, this whole family of functions that satisfy the differential equation part, we've selected the exact member of the family that passes through this point, or that when you plug natural log of 3 in for t, you get out 1 over pi for y.